Hello, Greg Latta here, Able 8 Victor, and today I'd like to talk to you about the Pi network. Pi networks are used in just about every amateur radio transmitter that came out after World War II, up until the solid state era. Not only transmitters, but amplifiers as well. The Pi network transforms the high impedance at the output tube to the low impedance down at the antenna. Before World War II, a type of circuit called a link-coupled circuit was used to do this. That's because before World War II, open wire line was the predominant transmission line, and the link-coupled circuit was perfect for that. But after World War II, coaxial cable became available. Coaxial cable has one side grounded, and the link circuit doesn't have one side grounded. It also turns out that the link circuit permits a lot of the harmonics generated in the final amplifier to get through to the antenna. And that was a big problem in the early years of television. The slightest amount of harmonic radiation wreaked havoc with the early television receivers. The Pi network came out because it could attenuate some of those harmonics, and furthermore, one side of the Pi network was grounded. The Pi network was also relatively inexpensive. A couple of variable capacitors and a coil were all you needed, and you could tap the coil and have a band switch and switch bands without having to open up the transmitter and unplug a coil and plug in another coil. So the question is, how does a Pi network perform its magic? To understand that, we have to look at two things: a parallel resonance circuit, and also what happens when two capacitors are in series. Now, a parallel resonance circuit is used throughout radio, and it means simply that we have a coil and a capacitor connected in parallel, like that. What's neat about this is that if you were to charge up the capacitor and then suddenly connect it across the coil, the capacitor will start to discharge down through the coil, and eventually the current will start to drop. However, while the current is going through the coil, a magnetic field is produced around the coil. And then, as the current starts to drop, that magnetic field collapses and induces an EMF or a voltage in the coil that tends to keep the current going. It's like electrical inertia. And what actually happens is it causes the capacitor to charge up the other way. And then the cycle repeats. The capacitor starts to discharge, the field in the coil builds up, it starts to collapse, the capacitor charges the other way, and we get a looping current here that is in the form of a sine wave. The energy in the capacitor goes from one form to the other, back and forth, and we get a sinusoidal vibration. By varying the capacitance, we can control the frequency of that vibration. Now, it doesn't last forever, because there's a little bit of resistance in the coil, not much, but there is, and so eventually the vibration dies out. However, if we can whack this is very much like a swing. If you have a mechanical swing, or equivalently a pendulum, if you pull the pendulum aside and let go of it, the pendulum will swing back and forth. This is a mechanical equivalent to our parallel circuit. Here the energy goes from electrical to magnetic and back and forth. Here it goes from gravitational to kinetic and back and forth. This won't run forever. Friction with the air, stretching in the string, it's going to eventually run down. But if you give it a little bit of whack each time, just the right amount, you can keep it going. In fact, it's more amazing than that. If we use a really big pendulum, one that all of you have probably sat on, we have a swing. And if you put a weight on the swing and then start tapping it, don't pull it aside and let go of it. We're not going to start it that way. We're just going to tap it. First of all, if you tap it really fast, nothing happens. If you tap it really slow, nothing happens. But if you tap it at just the right frequency, in other words, if you tap it at the resonant frequency, the energy of each tap gets stored, and eventually a big vibration builds up, even though you are putting the energy in a little teeny bit at a time. A very slight driving force results in a large oscillation of the swing. And in fact, if you overdo it, you can make it swing too far. The same thing happens here. If we can somehow push this thing a little bit each time, and the way we do that is by hooking it up to a radio frequency amplifier. And if this happens to be a Class C amplifier, which most CW rigs, like novice rigs, most CW rigs are Class C amplifiers. In fact, AM transmitters have Class C amplifiers. What's coming out of the final amplifier tube is not a sine wave. What's coming out of the final amp tube is actually a sequence of pulses. It's acting as a switch. The tube actually acts as a switch, and we have a sequence of pulses coming out of this thing. When those pulses hit this, they essentially whack it, just like pushing on the swing, and we get a circulating current here that builds up, and it is much larger than the voltage that is driving it. The voltage that builds up across the parallel circuit excuse me, is much larger than the pulses that are driving it. It stores energy. And this is in fact called a tank circuit, because it is a tank that stores radio frequency energy. If you put pulses that are too big, it is possible, especially in a high-powered amplifier, to get the amplitude here so high that the voltage gets high enough to arc over in the capacitor here, or arc to ground, or you can actually damage the final amplifier tube. It's very important not to drive this very hard in this case. This is what we call unloaded. A huge voltage can build up in this particular situation. Some energy is lost in the coil and in radiation, but it's very small, so you can't turn this up very far. In fact, let's make this variable. Let's make that variable. So we barely turn this up. You never operate a transmitter like this. Notice there's no antenna connected to this. There's no load. You never operate an amplifier or a transmitter without a load. We're talking about a laboratory experiment. Big voltage, much larger than the driving voltage, builds up across this circuit. And we're going to use that. Now, the other thing we have to look at is how capacitors behave when capacitors are in series. let us apply an alternating current. Now in this case we use a sine wave generator. We don't drive this with pulses, we drive this with a sine wave signal generator. In this case we find that the two voltages across the capacitors add up to the total voltage. However, they do not add up the way they do with resistors. Let us suppose this is a 100 picofarad capacitor, and let's make this a 1000 picofarad capacitor. Because with AC, capacitors act oppositely of the way resistors do. The larger the capacitor, the easier it is for the AC to get through. The reactance of a capacitor is lower the larger the capacitance. And so what we find is that if we had resistors, if we compare this to resistors, and suppose this is 1K and this is 10K, and we connect this to a source, we would find that because this is 10 times the resistance, we'd get 10 times the voltage across this one that we get across this one. That does not happen here. What actually happens is, because this one is 10 times larger, we get 1/10 of the voltage across this particular capacitor. The bigger the capacitor, the lower the voltage across the capacitor. Now we're assuming that the current through these is the same, and if they're connected like this, it is true. So for instance, if there were 100 volts across this capacitor, we only get 10 volts across this one because it's 10 times larger. Now in our pi network, strictly speaking, this is not how the capacitors are connected. It looks like they are, but it turns out this assumes that the current is the same through both of them. In the circuit that we're going to come up with, it's not, but the idea is still the same. As a matter of fact, we can vary the voltage across this midpoint by putting two capacitors that are adjustable in series like this. And if we make this one big and this one small, we get a small voltage here. If we make this one small and this one big, we get a big voltage here. We essentially have what's like a sliding tap on a coil, except we're doing it with a couple of variable capacitors. And we are going to put that to use. However, the formula that is used with capacitors like this will not apply in the case that we're going to put this through. Okay? So just remember that. All right. So here's what we got. We've got high voltage, low current pulses coming from the final amplifier tube. What we need is a sine wave, first of all, and second, we need to somehow lower the voltage because our antenna needs lower voltage and higher current. Here we have high voltage, several hundred volts typically, and low current. The current depends on, of course, the power level, as does the voltage. Down here we need relatively, here's our load, this is our antenna, and we'll make that 50 ohms. And for that, we need relatively low voltage at correspondingly higher current. How do we change the high voltage at low current to lower voltage at higher current? The answer is we store energy here in this parallel resonant circuit. How do we get the lower voltage? Well, one way to do that, we could do this, is we could connect this across, and we could use a roller inductor. And this way, we can control how much across the coil we tap our 50 ohm load. The more coil that we select, the higher the voltage here. And what we want to do is find the tap point that's just right, so when we run this at full power, we get the same power going into the load, so the energy goes in and then comes out, but at a lower voltage and a higher current. And how do we get a higher current? Because we keep putting current in here, and it builds up and it builds up. The current circulating in here is bigger than the current that's going into it. You're storing energy in here. You could do this, but roller inductors are expensive, very expensive, and difficult to implement. Maybe there's another way to do it. Instead, what if we replaced this one capacitor with two capacitors in series? Okay? We are going to replace this with two capacitors, two variable capacitors in series with each other, like that. Now, we still have to adjust these so that it's at resonance. And one way you do that is when it resonates, you'll notice that the plate current in the final amplifier tube typically dips down. Also, your output goes up. That's how you know that you're at resonance. Well, we can connect our load resistor here across this capacitor. Here's our 50 ohm load resistor. What we can do now is feed in the energy, and first we feed in only a little bit. And we start with this capacitor almost completely meshed. That means very little voltage is going to be developed across it. Very little voltage is going to be across the load resistor, and very little power is going to go into the load resistor. Then we adjust this so we get resonance. We get a dip in plate current, or we see a maximum coming out into the load. Then we open this capacitor up a little bit. We reduce its capacitance. And then that puts more voltage across it, more voltage across the load, and more power goes into the load. We're going to have to readjust this capacitor each time we do this one. When we lessen the capacitance here, we're going to have to increase the capacitance there to compensate. So we open the loading control, which is what this is called, and we redip and adjust the plate tuning control to keep resonance. And we continue to do that, and also while we do that, we can increase the power that we put into it. And eventually, we will get to the point where the voltage here across the load resistor is such that the power absorbed by the load is exactly the same as the power coming out of the final amplifier tube. And that's what we call a matched situation. Now, there's a problem here. First of all, I remind you, you cannot use the usual formula for dividing voltages with these two capacitors because the current through them is not the same. The current through this one is reduced because of this load here, and that means that they are not in a situation where the current through them is changed. The other problem with this is that this capacitor, you'll notice, has both ends above ground. Normally, our final amplifier tube, one side of it is connected to ground. And this means we'd have to somehow specially mount this capacitor. Well, you know, you can drive this. You don't have to connect the driver across the whole circuit. You can hook it up to part of the circuit and still get that ding in there to keep it going. So we can make this easier to build by instead connecting our generator to this point here, to this point there. This will send a current pulse through this capacitor, and that's enough to keep that circulating current going and to feed energy into it. You don't have to feed it across the whole thing. This will still work. And by varying this capacitor relative to this one, we can effectively move the tap point on the circuit to that which gives us the right voltage here to give us full power here and full power there. That's what we're looking to do. If you've ever tuned up a transmitter, you might recognize this procedure. You apply a little bit of drive, you close the loading capacitor. This is called the loading capacitor, and this is called the plate capacitor or the plate tuning capacitor. You apply a little bit of drive. This is your antenna here. You dip the plate current, or you put your watt meter here and you measure the power going out and you maximize the output. You open this a little bit, you open the load control, you redip this, you open, you redip, you open, redip, and generally you do this until you reach rated output. Believe it or not, I know that doesn't look like it, but that is a pi network. This is a pi network. I often tell my students to learn to take a schematic diagram and rearrange the schematic diagram. Many schematic diagrams are drawn by artists and draftsmen to get everything on the page. And sometimes the parts aren't laid out in the schematic diagram in what I call a logical manner. Things going in at the left, things coming out at the right, and so forth. All you have to do here to make this look correct is simply redraw it. So let us do that. To redraw our circuit, first of all, let us note that the bottom of our final amplifier tube here, that circuit, that's grounded. So we can ground that, and that's not going to affect anything. Now, we start by drawing our final amplifier tube, our source of power, our power source. And you notice we come up and we come over to a junction between the coil and a capacitor which is connected to ground. So we have a capacitor here that is connected to ground. Then we have our coil. The other end of the coil is connected to another capacitor which is also connected to ground. It's also connected to our load, which is connected across that capacitor, and then that comes back to ground. If I now you can see that what I in fact have is a pi network. And let's label this. We can connect all of these ground points to emphasize things. So I'm going to actually connect wires here and then connect this to it. And I want to do that because now you can see that the circulating current is occurring here. The parallel resonance circuit is these two capacitors in series along with this one, and those two capacitors are connected in parallel with our inductor L. And that is, in fact, a pi network. In fact, you might want to know why it's called a pi network. Where in the world do they come up with that particular name for it? Because when you draw it with the ground connections here, the middle part looks like this. And that has the shape of the Greek letter pi. This is the top of the pi, this is the sides of the pi, and that is why it is called a pi network. It is a very useful circuit. To use it for band switching, it's very, very easy. All you have to do is add a switch here on the coil. We can select different parts on the coil and have a switch that can hook up different portions of the coil, and we can easily switch this from one band to another by selecting a larger or a smaller coil. So I hope that helps explain why you tune up one of these transmitters the way you do, and why it is used so much. Essentially, again, we start with the load capacitor fully meshed, and that is essentially shorting out the load, and we have very little voltage across the load. We dip the plate current or peak the output with the plate capacitor to bring it to resonance, and we have this circulating current here, which is much larger than the current going out, okay, and the current going in. Then we open the loading capacitor, which increases the voltage across this capacitor because you're decreasing the capacitance. More power goes to the load. You have to readjust this to bring it back to resonance because you have changed the capacitance across the inductor. And you continue opening the load until finally you just reach that point where you have full power here that equals the power that's going in from the final amplifier tube. And some folks say, including me, you ought to go just a little bit tad further because that makes sure that you keep things in a nice operating mode. I hope this helps. If you like the video, please make some comments down at the bottom there here on YouTube. And if you find this useful, then I'll do some other ones in the future. Take care, and you might visit my website at greglatta.com. Take care. 73.